In this lecture, we're going to talk about fractions. Fractions are not strange. These are the numbers in the format of, for example, 3/5. It's a fraction. So fraction is kind of the first of a type of composite numbers, meaning that a fraction is really a number divided by a number. So for example, 3/5 really means it's a 3 divided by 5. But the first thing I want to make sure that we are all clear is a fraction is a number. And a lot of times we forget about this fact. It is a number. It's a one number divided by another number, but the result is a number. Being a number, we can represent a fraction onto a number line. For example, if you look at the number line of here, so the middle is 0, okay, and the right side is positive. 1, 2, 3, and on this side, of course, is -1, -2, -3, and so on, this. So for 3/5, this number is going to be represented somewhere, because you do 3 divided by 5, the number is going to be less than 1, but the number is also bigger than 0. So this number is going to be somewhere here. And how you're going to really represent this number is you're basically using the denominator 5, you divide the 0 to 1 into 5 things, and 3/5 is at this point. Okay, you count 3 such sub-intervals, small intervals, and you get 3/5. So fraction is a number, and in this number, for example, I'm still writing 3/5, the top one above this bar is called a numerator. It's a numerator, and number below the bar is denominator. So these are the usual format of a fraction. Now, certainly fraction can be other formats, other types. For example, I can even have 1.3 divided by 5.2, right? And of course, this is really it's 1.3 divided by 5.2. Okay, so these are other fractions. But for now, let's focus on the simplest fraction form, and usually we call such types as a fraction. As a usual kind of format is formats like 3/5. So we are assuming the numerator as integer and denominator as also integer. And let me write down the usual format: a over b. A is an integer. B is also an integer. And later you will know that this form is actually these kind of A is integer, B is integer. It's also known as rational numbers. Okay, but in here we're going to be using fractions and rationals almost as interchangeably. So we're going to focus on this form: A over B. A is an integer, B is an integer, and we call it as fractions. So we're going to understand how we're going to add fractions, subtract fractions, multiply fractions, and divide a fraction by another fraction. Basically, the basic operations of fractions. Being numbers, we need to understand how we do operation on them. And in this lecture, we're going to basically connect the fractions with the lectures we have done so far, namely the basic operations of integers and powers. Well, basically, going to review all those materials we covered onto the fractions, and you see that they are all interconnected. So surprisingly, it's actually for the fractions, the multiplication and division is easier than addition and subtraction. That's really a bit of a surprise. As we learn of integers, we learn the additions and subtraction first, because these are easily be countable. But fractions is actually the addition and subtraction is slightly harder than multiplication and division. So we're going to learn multiplication and division first. But first, let's understand, when is fraction multiplication usually used? Okay, and that's the case when we say there are 2/3 of something. Say 2/3 of A. This really means that we're taking A and multiply by 2/3. Okay, this is 2/3 of A. And when we say we want to double of A, we don't say 2 of A. We usually say twice of A, right? But when we talk about fractions, we say 2/3 of A. It really means that 2/3 times A. And when A is, let's say, an integer, 2/3 of integer, say 2/3 of 12, it really means 2/3 times 12. Right? And when A is a fraction itself, say 2/3 of 5/6, then it's really 2/3 of 5/6. So you see, when we introducing a fraction, we often first we really plug in something known, like A is an integer, and try to understand what this means, and then you extend this idea into A is a fraction, and you see that it's really defined as a multiplication of fractions, right? So this is often how this, different concepts are extended. You see this fractions of an integer can be extended to a fraction of fraction, and that introduces the multiplication of fractions. Okay, so first let's look at problem number 1, just to introduce this idea, or this idea of fractions, and trying to introduce the idea of fractions multiplication. So there are 30 students in a class. 3/5 of them are girls. 3/5 are girls. Question is, how many boys in the class? Okay, so this is a very simple question. Again, that, I hope you're going to figure out yourself first, and then let's see how I do this. All right. So one way is we're going to figure out how many girls in the class, and then we take the total number of students minus the number of girls, that will be the boys. So the idea is number of girls will be 30. 3/5 of all students are girls, so that's 30 is the total number of students, times 3/5. That will be the number of girls. And then we're going to subtract subtract the number of girls from the total number of students, and that will be the number of boys. So it will be 30 minus 3/5 of 30 is going to be 18, and that will make it 12 boys. Now there's something that I want to point out here is, when we have this problem, it's constructed that the 3/5 times 30 is going to be an integer, right? Because this is number of girls, and we're not going to have fraction number of girls here. So this is going to be an integer. What does that limits this fraction number? Of course, in here, this problem is constructed. But what this constraint on this fraction? If you think about it, it really means that the denominator of this thing, n30, has to have some relationship. In fact, the 5 has to be a divisor or a factor of 30. Okay, just give it some thoughts. You cannot just arbitrarily say 3/7 of the class are girls. It's not going to make any sense. Okay, let's have problem number 2. There are 3/5 of a class. In a group of students, 3/5 of them are girls. So this is kind of the opposite of the problem number 1. 3/5 of a group are girls. If we know the number of boys in a group, is 24. How many students are there in the group? Okay, so if there are 3/5 of the group are girls, and the number of boys in the group is 24, so first we figure out what's the fraction of a group are boys, and that would be 1 minus 3/5. Okay, we would not really have learned fraction of multiplication, subtraction of fractions yet, but this is simple enough, so we know that it's 2/5. Okay, so just skip a little bit, and 2/5 going to corresponding to 24 students, and we really want to figure out in effect, 2/5 corresponds to 24. What is 1 corresponding to? So if you think about 2/5 is corresponding to 24, the total number of students is going to be corresponding to 1. What's that going to correspond to? Right? That's your real thinking. And the idea of this is, one way to think about it is 2/5 corresponds to 24. So that means 1/5 is going to corresponding to 12. Okay, and 1/5 corresponding to 12 is 1 going to corresponding to 60. Because we're going to multiply 5 on both sides, you get 1 corresponding to 60. Okay, so that's the way of thinking about it. Another way to think is actually you using this notion of introducing an unknown. So if you assume the total number of students is x, or let's using a box, the box times 2/5 going to equal 24. Okay, what's that box going to be? It's going to be equal 24 divided by 2/5. And that equal 24 times 5/2, and that's going to equal 60 as well. Now, how you know that is you're going to be using this divide? Well, once you see something that's kind of unknown thing, you can using an idea of similar idea. What if I have this, instead of a 2/5, this box times 2 equal 24? What's this box going to be? This box is going to be 24 divided by 2, right? So if you figure out when it's an integer, you do this divide, Well, for the fraction, you can do the same idea. And this idea of analogous and extension is always a very, very powerful idea for you to figure out basically new rules when you encounter something a bit of unfamiliar. All right, so we introduced the fractions when we're using fraction multiplication. And the last thing, problem number 3, is just a direct question about what is fraction multiplied by fraction. So problem number 3. What is 2/3 of 3/4? Okay, and that is really 2/3 times 3/4. And we're going to show how we do this, but that's the expression that we're going to write down. And we're going to see just slightly later that this is going to be equal to 2/4. The 3 cancel each other in this multiplication, and this can be simplified as 1/2. Okay? All right. So now we're going to introducing fractions multiplication. For two fractions a over b and c over d, the rule for multiplication is really simple. You're going to multiply the numerator together and multiply the denominator together. Okay, a times c, b times d. And why is that? Let's do a bit of using the techniques that we have done in the operations. So a over b is really a divided by b times c divided by d. But we know that division is really multiplication of the reciprocal. So a divided by b equals a times b 1/b times c times 1/d. And next, we're using the commutative property, and this equals a times c times 1/b times 1/d. And then we're using associative property. This equals this multiplied and this multiplied together. This equals a times c divided by b times d. All right, so we have this rule. The simple rule goes is just the numerator multiplied together, denominator multiplied together. And that's how we do fraction multiplication. Okay, division of fractions is equally simple. A over b divided by c over d. This equals a times 1/b divided by c divided by d inside. And this equals a times 1/b times 1/c times d. And this equals a times d by b times c. And this division is going to be, if I simplify it, it's really equal this. Divided by c over d equals a over b times d over c, the reciprocal of this. And then using this formula, this rule, a times d, b times c. So you see that we're building on top of each other to get the rule for division of multiplications. And let's look at the power rule for fractions. We learned the power in the previous lectures. So what is a over b to the power n? N here meaning positive integers. And this equals, remember the definition of power is just the same number multiplied by itself over and over n times, right? N times. And that, if we're going to do this multiplication, the first two numbers and then the next two numbers, it's going to be equals a squared times b squared times a over b times a over b. Now it is only n minus 2 times. And if you're going to continue this, it's going to be all the numerators multiplied together, a times a, n times, and b times b, n times, which of course equals a n to the bn. So for fractions, if you raise a power, it's the same as you raise power of the numerator and raise power of the denominator. So let me write down this clearly. A over b to the power n equals a to the power n divided by b to the power n. Okay, so that's pretty simple. Now let's look at problem number 4, a problem of multiplying a bunch of fractions together. And it's going to illustrate an important point when you do multiplication of fractions. The problem is calculate 1 over 2 times 2 over 3 times 3 over 4. Okay, just take some time to do this problem. Assuming that you have done it, let's look at multiplication of fraction a over b times c over d. Remember that this equals a times c, b times d, right? And often, if you're going to really do the numerator multiply together and denominator multiply together, this is not the most efficient way. Often you will see that c and b maybe has some common factors, or a and d has something common factors. You want to cancel those factors first before you do actually the multiplication. So for example, the problem that I showed before, 2 over 3 times 3 over 4, this is really equals using the changing the order of operators. This is equal to 3 times 1 over 4. This is equal to 2 over 4 times 1 over 3 times 3, right? And this equals 1. So it kind of cancel each other. So the basic fact is, if you are seeing common factors, for example, this 3 and the 3, if you see the same number appearing in the numerator and denominator, you can cancel. If you see some common factors between the numerator and denominator, you also can cancel. So there's a factor of 2, I cancel here, and divide by 2. So this is all using the same fact. A over b times n over n, where time a 1 basically here. This equals an times gn. And this n can be integer or can be anything, as long as it's not 0. Okay, when it's 0 over 0, it's undefined. But as long as it's not 0, you can multiply the numerator and denominator by the same number. And this does not change. Okay? So which means that I also can do the division as well. A over b equals a divided by n, b divided by n. Basically, we're multiplying still n over n. So basically, we can extract these some common factors out. That reflects this to this 2 over 3 times 3 over 4 is we're basically removing the common factors first, and that does not changing the fraction. Okay? So for problem number 4, when we come back to this, is if we see common factors in here, of course it's constructive problems. The 2 and the 2 are the same, so you cancel each other. The 3 and the 3 are the same, you cancel each other. The 4 and the 4 cancel. All the way to 9 over 9, you cancel each other. What's left? It's going to be just 1. The first term you did not cancel, and the last term you did not cancel. This is 1 over 10. Okay, and this is a very important fact. So let me write down this. For a fraction, a over b If I multiply by n over n, which is really multiplied by 1, this does not change the value. It's going to be a times n, b times n. This is the same fraction as a over b. So the meaning of this is, if actually I take a fraction and I zoom in or zoom out the numerator and denominator by the same amount, the fraction does not change. And this has some connections with, actually it's exactly the same as, think about you're taking a shape and you zoom it. Okay? And when you zoom it, you know that you understand this as a similar triangles. So if you start with A and B, let's say the A and B are some length on the smaller triangle, not necessarily the sides, okay? It's A and B can be, arbitrary small, arbitrary big, does not really matter. And if I zoom it by n times, and this b by n times, right? That's how it's zoomed. Then this ratio does not change. It's a property of similar triangles. A over b is going to equal the zoom amount, a times n divided by b times n. So this fractions has a very deep connection together with similar triangles, which we are going to learn sometime later. Okay, but this property now leads a little bit problem. So for a fraction, say equal 1 over 2, this is the same as 1 times 2, 2 times 2, equal 2 times 4, right? Also equals 3 over 6, also equals 10 over 20, also equals 100 over 1,000 over 2,000. So for a fraction, there are many different forms, actually infinite different forms, to represent the same fraction. They all have the same value. Now, which way will be the right way to write it? Of course, in terms of values, they are all the same. But we don't like this kind of confusions, right? Think about in a test, like the actual answer is 1 over 2, but different people write down different things. They write down 3 over 6 or write down 1,000 over 2,000. Now, should you think that they are all correct? Of course, the values are all correct, but for us, better to see, and actually numbers are used for communication. For clarity in communication, we need to define a canonical form to represent fractions. And the form that most naturally is going to be saying that some kind of a simplest form. So for example, over 2 over 4, that's not the simplest form because what? They share a common factor. So this can be reduced to 1 over 2. So that leads to a very natural definition. It's called the simplest form. Simplest form fractions. A over B is simplest if and only if when A and B does not have any common factors other than 1. So, of course, the common factor is GCF. The greatest common factor of A and B is GCF equals 1. Only in that, if GCF equals 1, then A and B over B is simplest. Okay? The definition is very clear. Intuitively, we want to remove any common factors between the numerator and denominator, and that reduces to a form that we cannot reduce anymore. And if A and B are integers, that's certainly a well-defined quantity. Okay, so to find simplest form, it's clear that we need to find the greatest common factor between A and B. So if I give any any fraction, let's say 12 over 27. How we're going to reduce this to the simplest form? The idea is we're going to find the greatest common factor of 12 and 27. Let's say this number is m, okay? And we're going to show how we're going to do that. But let's say we find the greatest common factor of 12 and 27 is m. Then the simplest form is going to be, we're going to take the 12, remove the m from the numerator, take the 27, remove the common factor, remove the m from 27, and this form will be the simplest form. And in this case, GCF 12 minus 27 is 3. So 12 divided by 3 is 4, and 27 divided by 3 is 9. So this equals 4 and 9. And you see, by the definition of the greatest common factor, the 4 and 9 cannot have any other factors than 1 anymore, right? All the factors are captured in this greatest common factor, which in this case is 3. Okay, so the remaining of the class, we're going to focus on how we find the greatest common factor between numbers a and b. Or actually on the form, on the handout, we use m and n, but does not matter. So the fraction is m over n. And we want to find out the GCF, the greatest common factor of m and n. One simple method is due to Euclid, a Greek mathematician who was in around 300 BC. And the method, the Euclid method, is based on one fact. If m is a multiple of k, n is a multiple of k, then m minus n is also a multiple of k. Okay, the fact is very, very simple, right? If m is a multiple k, so it's like k times something. N is a multiple k, n is k times something. So then m minus n is going to be k times something minus k times another thing. So if you're using the distributive law, take the k out, it's m minus n is going to be k times something, which all those somethings are integers. All right. So now if we want to find out the GCF of m and n, the GCF of m and n is going to be a divisor of both m and n by definition. So if m is a multiple of that number, let's say this number is the GCF is, let's call this number d, okay? So if m is a multiple of d, n is a multiple of d, then the m minus n, or n minus m, is also a multiple of d. So that's equals GCF of n and n minus m. If m is bigger than n, then we're making this m and n, this pair m and n, smaller by using the smaller number n and then using the difference of m and n. Okay, so for example, the 12 and 27, the GCF of 12 and 27 is going to equal the GCF of 12 and 15. I'm always taking the smaller number and then using the difference of that, the bigger number minus the smaller number, so 12 and 15. And we can continue this. The GCF 12 and 15 equal GCF of taking the smaller number 12 and then taking the difference of the bigger number minus smaller number, so it's 3. Now for GCF of 12 and 3, it's obvious, right? If you have two numbers that if one number is a multiple of another number, then the GCF is going to be the smaller number. So this is GCF going to be 3. Okay? And this is the Euclidean method. Let me recapture a little bit. The GCF, the Euclid method, the GCF of two numbers, m and n. Let's assume m is bigger than n in this case, okay? And we want to reduce this one to a smaller problem by taking GCF. This is going to be the same as GCF n, which is the smaller number of the two, and the difference of the two. And we're going to continue to do this until the GCF is obvious. Until when GCF is obvious. For example, when you have the two numbers are, one number is a multiple of the other number. So then in that case, the GCF is going to be the smaller number. Let's using some examples to get familiar with this idea. So let's say we want to calculate GCF of 56 and 182. This is going to be GCF. Okay, always keep the smaller number, which is 56. And the difference between this and this is going to be 126. Okay, continue to do the same step. GCF, take the smaller number, which will be 56. Take the difference, that will be 70. And then this equals GCF of 56. Take the difference, will be 14. And in this case, the GCF of 56 and 14, you realize 14 is a multiple of, is a divisor of 56, so this equals 14, and you're done. Okay, next question. Find the GCF of 2016 and 2772. This is going to be GCF of 2016 and 756. And this is GCF. Take the smaller number, which is 756. And then this is 1, I hope I'm getting this right, 60, correct? And this equals GCF of 756, 504. And this is GCF of 504, 252. All right, and this equals 252. Wow, interesting. So you see, because 504 is 2 times 512. This is the Euclidean method. Can we improve it? Because you see that when the two numbers are very large, this step of taking the smaller number and using the difference can go many, many steps. There's certainly an improvement of the Euclidean method. And that's it's just modified Euclidean method. I'm now going to prove it. But it goes like this. The GCF of m and n, again, we assume m is bigger than n. Still, we're going to take the smaller number, n, but the other number is not going to be using m minus n. Instead, I'm going to be using m divided by n, the remainder of that. Okay, if the remainder is 0, then of course this is GCF of n and 0, it will be n, because when the remainder is 0 means that m is a multiple n, that GCF of m and it should be n, right? Otherwise, we take the remainder. Intuitively, what we're doing is, instead of we're doing the m minus n, like many steps of m minus n, next one is m minus n, we want to find out the largest n such that largest multiple of n, let's say kn, is still less than m, and we find out the remainder of that, m minus kn. So we're doing m minus n minus n minus n, so many n's, such that this m minus thing is the remainder. And then with GCF n and the remainder of m divided by n. Let's use an example to see that clearly. So for example, let's still using the GCF of 12 and 27. Okay. So this equals GCF of 12. So the original Euclid method, we're going to take 27 minus 12, correct? But in here, we're going to using 27 divided by 12, the remainder of that, which is going to be 3, and that going to be 3. So it's much quicker this way, especially when the difference between 27 and 12 is a large number. Then the Euclidean method is going to do several steps, and this modified method is going to compress all those many steps into one step. Okay, the last thing I want to talk about is a different way of calculating the GCF of m and n, and that is using so-called long division. So the idea is the following. We have m and n. We first find out what is the smallest prime number that is divided both m and n. Let's say this is p. Okay. The next number is we divide m over p, n over p, and then for these two numbers, we continue to do the same process to see if there's any prime numbers is a factor of both these numbers. If there are, just keep doing it. Let's say it's a cube. Okay, and we keep doing it until there's no common factors, and then the product of these going to be the GCF. And this method is closely related to prime factorization. And in next lecture about fractions, we're going to go over this. But here, let's again look at this example of 12 and 27. The idea is we're going to find out the first prime number that is a common factor of 12 and 27. So is it 2 a common factor? No. 3? Yes. So 12 divided by 3 is 4. 27 divided by 3 is 9. And in this case, there's no any other prime factors, common prime factors for 4 and 9. So this is done. And this is going to be the greatest common factor. So okay, so we described the greatest common factor, and don't forget about the fact why we are talking about the greatest common factor of GCF of m and n. The whole idea is we have a fraction of m over n, or actually in this case n over m, does not really matter. We want to simplify this number into the simplest fraction. And to simplify this, we have to find out the greatest common factor between m and n, and we want to remove that. So m going to divide by GCF of m and n going to divide by GCF of m and n. Only after we remove the common factor, this is going to be the simplest form of fraction. And that's the whole purpose of finding GCF in this case. All right, and this will be the end of this lecture.